Oh. Hi. So, all right, perfect. I got a signal that it's time to start. And first of all, thank you all for coming to this talk. My name is Raphael. I'm a software consultant in Oslo, in Norway. I'm a German though, so I'm not a fellow Scandinavian, but I'm really glad to be here. I'm talking today about runtime code generation, or in the end, I want to convince you all that Java, at its heart, is a dynamic programming language to some extent. And I'm using this principle a lot, so I'm writing a library called Byte Buddy, which I'm going to talk a bit about today, and I'm also maintaining a library called cglib, if you have worked with that, and I'm also helping out on the Mockito project. And all of these libraries build on the assumption that Java is fairly dynamic, and that's what I'm going to try to show you today. But such that you understand what I mean by that, I want to look at an example with you first. So before we dive into runtime code generation, I want to show you how it is used, and I'm trying to build a small library with you now. Don't be scared, it's not much code, it's more about the principle. We're trying to implement a security library, such as Spring Security, and I'm mentioning Spring Security because obviously if you know Spring Security, the APIs are quite similar. So what we're trying to do is we want to have an annotation. In this example, it's called secured, with an attribute which is called user. And we want to use this annotation on methods, and we want to tell the Java virtual machine that whenever a method is secured, the method should only be invocable if the user holder, in this case, has a user logged in that equals the attribute. So in this case, we start with anonymous, which is the default user in our framework, and we want to have like a service like this one, and we have this very sensitive method, right? And we want to make sure that only administrators can ever call this method, right? So, and that's basically the setup. That's what we want to implement. And here we have a problem because the Java virtual machine doesn't process annotations. Annotations are in the class files, they're metadata, but they don't trigger any execution path. So the JVM won't do anything just because there's an annotation. That's something we have to do. And that's where runtime code generation will come in. We'll see that in a second. Right? Because if we want to implement this library, what would we do? How could we solve this problem, right? The first problem we have is that we implement a framework, right? So the framework doesn't know about the service necessarily. So the framework promises to secure any type we give it, but the framework doesn't necessarily know about this type, at compilation time at least. Because we have two jars, right? We have Spring Security, and we have your framework, and Spring Security doesn't know about your framework. You can't call Pivotal and say, look guys, I have this new service, please update your library to support it, because that's not the idea, right? So the library doesn't know about your service, but your service knows about the framework, and it should be the other way around. But obviously at runtime, both libraries end up at the same class path, right? We have these two jars, and they come together for the first time, only at runtime. And that's why it's not only about code generation, it's about runtime code generation. That's what makes it so important, right? So, given, or let's just assume for a moment, we can change implementations. And we can, as we will see. How can we implement security in this case? Well, the easiest way to do it would be just redefining the method, right? How can we implement security? We have the annotation saying admin, so we have to just add a small if, right? We say, if admin doesn't equal the current user, then we throw an exception. And as a consequence of that exception being thrown, we will never touch the code that does the deletion logic, right? So that's how easy it is to do a security framework. That's all we need to do. The only thing we have to find out is how to do it. And there's ways for it. There's like build time instrumentation, so you can have a Maven plugin that, for example, puts this if into your source code before you compile it. Or there's Java agents. We're going to look into Java agents for a minute in the end of the talk, right? The more typical way of doing things, and that's how Spring Security does it, more or less, is however not redefinition, but it's list-of substitution. And list-of substitution, in a way, is we create a subclass where we override the method. And the overridden method does just the same check that we just shown, where we check the current user against the admin string, and if that's not the user we expected, we throw an exception, and we never call the super method as a consequence, because we exit the method. As a consequence, the method is secure, and this is really the first step of why Java is a very dynamic programming language. Every call site almost is virtually dispatched, right? So at runtime, The classes come together and they bound. Spring, if you define a Spring bean, right? Do you get an instance of the class that you have defined? No, you don't. You get a proxy class that Spring creates for you, where Spring injects all the logic for you. Like transactional, for example, you will have something like that, where a transaction is opened, the super method is called, and after returning from the method, the transaction is closed. Same goes for the secured annotation, or goes for metrics annotations. All of this is done by runtime code generation, and that's why it's worth knowing about this. You all do use runtime code generation. Every enterprise project does use code generation, and it shows in the download numbers, right? These libraries that I work with, they're not very known, they're not famous in any way, but they're very heavily used because it's a neat little tool. By themselves, they do little, but they can enable very powerful implementations. Okay, so let's do some Java 101, and then that's where the dynamic part, I think, comes out the best. So how does Java work? How does a Java program work? You write a program, you use Java, or you use Scala, Groovy, JRuby, Clojure, Kotlin. There's an endless list of languages on the JVM. And how do they all work on the JVM? It's by compiling to so-called Java bytecode. So Java bytecode is an abstraction layer between the Java virtual machine and the hardware that's basically running the code. But bytecode, in favor over machine code, is standardized. And that's the reason how all these languages can interact as well. Java can call a Scala method, as in theory at least, or the other way around, because bytecode is the only common language that is spoken on the JVM. Even if you write a Java program and you bind your code to another library at compile time, you are basically looking at the bytecode of this library. You don't even need the source code. And this bytecode is more or less a universal language, and it has very little information already about how it is actually executed. A Java class is a very loose concept, right? It's not even linked. The linking happens at runtime. And that enables you to basically, if you happen to intercept this linking process, that you can just inject any code anywhere in your program where you want to, and that's basically opening up for Spring, for Hibernate, all these libraries to do what they're doing. So bytecode itself is sort of a machine code abstraction. It's very high level still, but it's machine code for a Java virtual machine, right? And a Java virtual machine is not an actual machine, it's a virtual machine. So the machine code, which is bytecode, is also rather virtual. But at runtime, it's loaded by a class loader, and it's then first interpreted in hotspot at least, and then it's optimized. And that's another important factor. Compiled Java programs are not yet optimized. That's happening at runtime, so we can actually do runtime code generation without having a performance trade-off. So doing code generation isn't changing anything for you, because your code that you generate will be optimized. In programs like C, or C-compiled programs, you have to take care of that if you manipulate a program, because you change the performance behavior as well. That's not true for Java, right? So what we can do for that is that at runtime, like Byte Buddy, which is my own library, so I'm putting a picture here, but you can basically think of any library, ASM, cglib. These libraries can create new Java code from a Java program. And that at first might not make sense to you, but if you think about it, then you can put a library in the class path that interacts with code that you did not even know at compile time, which is, in this case, the service layer from the perspective of Spring Security. And you cannot only create bytecode, since this format is standardized compared to machine code, you can also read bytecode, and then you can know what a program is doing. And you can also look into annotations, for example, and that's what these libraries basically are built upon. So you can read and you can create classes, and you're executed by the JVM. And if you look here, then you get a circle. Basically, you're writing a Java program that at runtime reads itself and then manipulates the program that's executed at runtime. So you know that at compile time, you don't have the necessary information, so you delay the process until execution time, and then you just run the program in the way you intended it when you have the necessary information. That's basically the idea of runtime code generation, and in dynamic languages, this is applied a lot. But then you have often naming conventions or whatever, like React, for example. How does React work? It discovers methods that just have a particular name. It's a contract in a way. In Java, you can do the same thing, more or less, but you use annotations, right, to interact. Okay. So, and then this is the point where people sometimes have objections, right? Why do you need to go that far? Java already has a means of interacting with code that it doesn't know, right? And that's the reflection API. The reflection API can do the exact same thing than runtime code generation can do. You can get a declared method by its name and its parameter types, and then you can invoke it with an object that is this reference and arguments, right? The problem with the reflection API is that it is completely untype safe. And that's where Java gets very verbose. There's a lot of checked exceptions, in the worst case, a lot of typecasting. You lose information that you actually have. And think a second about how this would work for Spring Security. If Spring Security didn't do runtime code generation, it would mean that you had some sort of abstraction, like a secure method call object, right? And you would give it, in this instance, you would give it an argument and all that, and then you could still do the thing. You could do the security check, you can read the annotation out, but as a result, you cannot behave, you cannot program towards your service, but you have to program towards the framework object, and that's something you want to avoid, right? You want POJO-centric applications, you want to keep this abstraction layer out of the business logic. And with reflection, you cannot do that. The great thing about code generation is that you can hijack a type of a user, you can inject your own logic, but the user program remains fully type safe. So you basically just opt out of type safety for the minimum amount of time that you need, and that's how you write a dynamic program. Using reflection in a way, you can emulate a dynamic program, but you lose all type safety. With code generation, you can have short segments of code that aren't type safe, in theory at least. They are still type safe since the JVM at runtime does check types, right? You cannot call a method that doesn't exist on an object, even if you cast it. But you can, for the user at least, project this world where all types are still safe and at compile time, right? Another point about reflection is also that it doesn't fail fast, and fail fast is important because you don't want to have this one routine that only runs once a month. If there's a bug in that routine, the reflection API would only trigger the error once the routine is run. With code generation, most of the time at least, you get an error at start time of a program, which is often the preferred way of finding out that something's wrong. And that's why this talk is also called Making Java More Dynamic, right? This slide first, right? You can also argue that do-it-yourself would be an alternative, right? You can just copy-paste this check inside of every method that you want to secure. But then at least you have testing as an issue, and it's not a very clean abstraction, because this might just be the start, right? You can have a security handler, you might have a metrics interceptor, you might have transactional interceptors. By doing this form of declarative programming and keeping the method clean to the business logic, you can separate your program much better, right? So this slide I thought would come. In JavaScript, for example, in applications like React, we have this sort of programming model all of the time. So this is nothing new. It's just a bit more complex to implement in Java because we have type safety, even at runtime. In JavaScript, however, we might have the same problem set, right? We have a delete everything method in some service object, and we call this delete everything method somewhere in our program. And if a framework is in between our code and the call side here, then we cannot be sure that this object actually is the object that we expected. So, right, this is duck typing. There's only the convention of the method name. And how do frameworks like React, how do they know that they have to re-render a page, for example? They know because when you call a method on one of or a function of one of your state objects in the framework doesn't actually give you back your object, your state object in React, for example. It gives you back a proxy where it sets some flag where it knows that if you called that method, you have changed the state of the page and it needs to re-render. So the framework always injects its own hooks into the code that you are supposed to be running because it needs to know something about your program that you don't want to put explicitly in there, right? So duck typing and code generation, in a way, are very similar concepts. And in dynamic languages, this is a lot happening. And it's also happening a lot on the JVM. Really, every framework of a certain size uses code generation. Like the Spring framework, I talked about that. Hibernate. How does Hibernate know that it has to load something from the database? Well, if you call a getter on one of your objects, it knows that now you are requesting an information. And if it doesn't have it, it doesn't just return an object, it has rewritten the method to go to the database, fetch the information, map it to an object, and return that object instead. The same goes when you call a setter. It knows that you have changed the state of the object, that it's something to flush back to the database once you're done with something, right? That's how Hibernate works. It's actually pretty simple. The same goes for Mockito. This is something I'm involved in. How can Mockito mock your classes? Well, we override every method to just return null, right? And if you change something, then we return something else. And we also record all the method calls so that we can verify it in the end. So this is all the magic. And everybody is doing it. Juice is doing it. Eclipse Link is obviously doing it. Play does it. Clover for how does Clover know the test coverage? Well, it rewrites your code to just have a callback into Clover every line of code, right? I've been here, I've been here, I've been here. That's basically it. Apache Wiki, Shiro, the OpenJDK even uses Cogeneration for Lambda expressions. Lambda expressions in the end are just classes that are generated on demand. You don't put it into the compiled code, because then at runtime you might do a Java update and Java might have new constructs available for Lambda, making Lambdas more performant most likely. So then they can just exchange it, and the next time you start up your program, the new logic generates a better class for your Lambda expression, right? Okay, awesome. So now we can use this for everything, right? So and I'm putting this in because unfortunately I'm active on Stack Overflow a lot, and I'm answering a lot of questions regarding Cogeneration, and this is the worst part of it. It's abused a lot as well, and it's abused in the context of performance. And performance on the Java virtual machine is a tricky beast in the first place, right? It's difficult to tell what things are doing. So a lot of performance work, unfortunately, is guesswork. And I've given a talk about how the JVM compiles code at Java 1 last year. So if you want to do this, I can obviously just refer you to that talk. I'm not going to go into details. But in general, what the JVM does is it takes your code, it reads it, just like as a code generation framework can read your bytecode. The JVM obviously also reads your bytecode. And then it tries to figure things out at runtime. And the JVM is something called a profile-based, has a so-called profile-based just-in-time compilation where it looks at actual behavior of your code. So the general rule or the general derivative of this is that you cannot outsmart the JVM. And it sounds obvious, and it is obvious, but people still try to do it. So an example is this, right? We have a method that multiplies some value I with a constant value. And as a C programmer, you might say, okay, this constant value, I want to inline that. So because it's out there. So what do? I go into the method, and I just rewrite it to put the constant value right into the compute method, right? So the program is faster, one level of indirection less. That's a pointer referral in the compiled format, right? But it's not. The bytecode is just a metaphor. Bytecode is more or less the programming language of the Java virtual machine. The Java virtual machine, ironically, doesn't know Java. The JVM doesn't know what Java is. It only knows bytecode. So a source code program to the Java virtual machine is fully meaningless. But it will take that bytecode and it will wrangle it, and it will wrangle it a lot. So never do these things. If you Google Cogeneration and performance, and you have like cglib for backwards compatibility reasons, we still have it, these fast class, fast method abstractions, right? The JVM has all that already. It does that better than cglib. Performance advice that was true for Java 1.2, 1.3 isn't valid anymore in the age of Java 8. So this old code, this older wise, just ignore it. Half of the stuff on the internet about cglib, about Cogeneration, is false as of Java 4, more or less. So it's been false for years, and people still apply this rule. So that's why I'm making it so explicit. One important part is reflection. Reflection is supposed to be slow, right? And reflection isn't fast. But what's slow on reflection is looking up a method, and it's mostly linked to the security model of the JVM, and it's about the state of the method instances. You know, a method is accessible or not accessible. So whenever you call getDeclared method, the JVM can only, or the reflection API can only return you a copy of the object, not the actual method it has linked already to something, right? Because you can change the state, and that might change the program somewhere else because you changed it to be accessible. So, and people like to say reflection is slower than generated code, or it's slower than native code. That's not true. What makes reflection slow, or what people think that makes reflection slow, is that reflection in original form is implemented as Java native interface, right? In the JVM, what it does, it reads your code and it looks through it and sees, okay, I can put this together, I don't need to do this is not necessary, so I'm not even running this code. But if you use JNI, the just-in-time compiler can only say, oh, C code, I don't know C, so I have to run it, right? And then that might block a lot of other optimizations. And if reflection really was implemented with JNI only, this would be a problem, because every reflective call, if you call a method reflectively that doesn't do anything, the JVM would normally do nothing, because that's the same thing for profile-based JIT. So the JVM has code generation as well. It will generate bytecode at some point for you, so you don't need to do it yourself. There's something that's concept is called inflation. You can actually set an inflation threshold. By default, it's 15. If you have called a method 15 times by reflection, the 16th call will be as if you had called it with the normal method call that you hard-coded. There's nothing to worry about. Yeah, so the JIT compiler knows its job. You cannot outsmart the OpenJDK team. You can try, but you most likely will not succeed. So, what's bytecode? This was the theory part. Now I'm diving into how you can do code generation. That's the more fun part. I hope so. I hope you can actually apply this for your project. I'm pretty sure you have use cases. But let's just look into bytecode, because in the end that's what we're messing with, right? So in this method we just want to add 1 and 2 and we want to return it. So how does this look? A bytecode program is just a list of instructions, and it's executed from top to bottom. And what the JVM is, or what the JVM abstraction is, and I'm stressing abstraction here, because this is not what's going to happen in hardware. This is just a metaphor you use to communicate your program to the JVM. In this metaphor, the hardware you're running on is a stack machine. And the stack machine, now you remember back the days you've been at university, is nothing that actually happens in hardware a lot anymore. Like my machine is not a stack machine, it's a register machine. But in the JVM, we have a stack, and then we push values on that stack, and we can pop values off the stack again. So in this case, iconst1 is just an instruction to push the number 1 onto the operand stack. And then 2 pushes the number 2 on top of that. Right? And then the iadd construction, you might guess it, pops the topmost values and pushes back the sum. Right? Now we have 3 on the stack. Then there's another instruction, in this case iReturn, which is popping the top value, which is now 3, and returns it to the caller of the method. And it's called bytecode because every number, every instruction has a byte assigned to it. So if you read up the Java Virtual Machine specification, you can find a listing of I think now 190 opcodes, that's how they're called, and where every opcode has a byte assigned to it and basically describes the expected behavior. And as long as you're coding to it, you can implement Scala just to do this, right? You can do this in Scala, you can add 1 and 2 in Scala, obviously. So if you compile a Scala program to do that, you will get the behavior at runtime that you expect. And yeah, what did I want to say? Yeah, in the end, this is all we need to do. It is tedious, but it's not hard. Bytecode isn't difficult, right? And if you compile a class with this method inside of it, you can open the class file with an hex editor, and you will find these 4 bytes. You will find 04, 05, 60, AC in a row somewhere, because that's the method body that's somewhere in there. And then you can use this hex editor, and you can, for example, change the 04 byte to become A5, and if you run that class file, you will have 2 plus 2 instead of 1 plus 2, and you just did code manipulation. Because in the end, code manipulation is mapping a byte array to another byte array, right? So there's libraries to do this more elegantly, to do it from Java. Instead of having to parse the class file yourself, you use basically what the stacks parser is to XML, ASM is to the bytecode format. And it's also a visitor API, so you will be able to basically have a visitor being called for every instruction you discover in the class file, but you can also just write methods. So in order to implement this method, we can just use ASM to have a so-called method visitor and call then visit ints iconst1, iconst2, iadd, iReturn. You just created a method dynamically. And there's a tree API as well, so you can also do it a bit more less efficiently, but more comfortably doing basically manipulating nodes. And then you have state, but you have to have it in memory. With the API, this is what most people use. You have the full performance benefit, but you have to do it in one pass, right? And that's great. Bytecode level APIs give you full freedom. You can do everything, and sometimes it's the right thing. I argue in 99% of the cases it's not the right thing, and I'll show you Byte Buddy next, and it's much easier than that. So even though I just told you what bytecode is, you don't really need to know it, because that's the biggest problem with ASM. Everybody in the team suddenly needs to know about the JVM, about the stack metaphor, and the JVM's type system is different to Java's type system. The JVM, for example, it doesn't know booleans, it doesn't know shorts, chars. The JVM just treats all that as ints, right? So none of the performance advice, you don't need to use shorts to make things fast. It's not happening. It's already erased at compilation stage. You might save some memory at some point, but certainly not inside of method bodies. But this is stuff you have to communicate to your team, and you don't want to do this. Also, it's very error-prone. You have to actually tell the JVM how big the stack is going to be, right? You have to tell it, I want to push 2 values, so please allocate 2 stack frames for me. With Java 6, the micro-optimization from hell, also known as stack map frames, was introduced, where you have to explain the JVM all jump sites inside of your method, because the JVM doesn't have if-else, it has goto. Good old goto. So this is also something you obviously don't want to deal with. And that's another irony. Bytecode level APIs are themselves not type safe. If you just switch the order of a method visitor call, you have things confused and you get the wrong results, and it's difficult to trace down. And it's very little expressive. Of course, 1+2 is better readable than the bytecode version of it, but you have the low overhead, and it's a very popular library, ASM, so it's very proven. BCL is an alternative. It's a bit better in some extent, but not significantly. And since the OpenJDK started using ASM, everybody is basically referring to it as the one and only framework. You have to watch out, though. Between version 3 and 4, this is the most asked ASM-related question on Stack Overflow is the version clash, because they changed the APIs a bit. All right, but I promised that you don't have to know any of that, and I'm just telling you because I want you to see the picture, right? This is where we go to a conference talk for, otherwise I could have sent you a link to some code example, and this is the code example I would send you. Byte Buddy, I have started Byte Buddy 3 years ago. I'm trying to replace cglib on the long run, because originally I tried to extend cglib, but the problem with cglib is that it was written back in the days of Java 1.1, and the code isn't pretty, to say it gently, and there's a lot of things that should have been done differently, which is true for every project that has been around for 16 years, and it's definitely true for an open source project where people hack in their nights and free time, where the thing with open source, right, is that the sparse resource is time most of the times, and cglib shows that now, unfortunately. So the original plan to transform cglib into a modern version, cglib 2.0, that's what Byte Buddy in the end became. So Byte Buddy is a domain-specific language, and I try to take known concepts from the Java language into an API such that you can relate to something that people already know. And Byte Buddy starts out with a configuration instance with its Byte Buddy. In this class, if you understand this code, I hope you do, then I did my job right. We say we want a subclass object, right? And then we want to take any method called toString. In this case, there's only one method that's called toString, which is object toString. We want to intercept it for returning the value hello world, right? So this is the Cogeneration hello world example. Now we make that class, and we load that class into the context class loader of the code that we're running. And then we're already in the reflection API that you might know. Now we can run this assertion here, where we say dynamic type, new instance toString. And that's going to be hello world, right? And that's what we wanted. Now you might guess how we can implement the security framework in the beginning that I mentioned, right? We will intercept methods that have a certain annotation, and we want to do something different when they are invoked. And then we can just subclass some user object, and then do something with them, right? And we can override the methods that are annotated and intercept. In order to do that, however, we have to do some more complex logic than just returning a fixed value, in this case, hello world. And this is where method delegation comes in, and that's basically the Swiss Army knife interception of most code generation frameworks. So what we do here is that instead of calling the method that we originally intended to call, we want to call another method. In this case, we just say delegate, so this is a static import, the class is called method delegation. So we say method delegation to my interceptor class. And my interceptor is obviously a class that you have defined. And in this case, it just goes to this class and finds any static method that matches the intercepted method best. So if, in this case, there's only one static method. So the resolution is trivial. In most cases, you only want one way to intercept a method, so you should, for your own sake, keep the resolution trivial. If you have more than one static method, Byte Buddy figures out a best match, which happens similarly to overloading. Basically checks all methods that exist, and it checks which method can take the most parameters, arguments, and then delegates to that. So, about arguments. This is still a hello world example, right? Now we can set a breakpoint. So if we call toString in this case, we will trigger the breakpoint in the hello world line here, but we still can't do much. We can, of course, now we can return a random value, or we can do a thread sleep or whatever. But in the general case, we want to do something with the method we're intercepting. So we need some context, right? And this is where Byte Buddy does a big distinction to what cglib does. And it's basically why I decided not to evolve cglib further, but to do something new. Byte Buddy works with annotations, right? Annotations don't have the best reputation among everybody, but they're a very neat tool, for this case at least, because there's something special about annotations. If an annotation is not present on the class path, this annotation is simply disappearing. The JVM will say, okay, this annotation type, I don't know it. So with an interface, what cglib uses, with an interface, you would get a no class def error. With an annotation, the JVM just swallows away the annotation altogether and ignores it. So it won't be there. In this case, you annotate the method parameter here with origin, and that tells the JVM, okay, I want, not the JVM, that tells Byte Buddy, I want to have a method instance injected into this method, and not just any method, but the method I'm intercepting. So here, this example will suddenly print hello world from toString, right? So if you intercept several methods, then you will always get the method back that you have just intercepted and prevented from being called. All right. So there's, of course, a bunch of annotations. I'm not going into... You probably want to learn about this when you're actually using it. Otherwise, I'll tell you and you'll forget. So just here a short overview. You can, of course, call the original method with supercall, for example. So supercall will just trigger the original method. And now you already can implement the framework, right? We have origin method. So we can read the annotation. Then we can check the annotation and throw an exception if it's improbable to call the delete everything method that we showed in the beginning. And otherwise, we have this callable supercall instance, and if you call, you will trigger the original code. So, bam, you've done your own security framework. It's probably going to be 10 lines of code. The rest the framework's doing for you. So much about subclassing. I'm going to try to look into something more advanced now, which is, however, much more fun to work with, and it's redefinition of classes. There's two ways of doing that, and the first one is using hot swap. And hot swap you probably know as a debugging feature of the JVM. Debugging feature that almost nobody uses because it's fairly limited, but you can actually do quite cool things with it at runtime. And Byte Buddy doesn't only allow you to subclass things, but it also allows you to redefine things, right? And in this case, we already have defined a class foo, and we already, so this code is run in this order, we already have created an instance of foo, and if we called the bar method, we would get the string bar out. So what we can do with Byte Buddy, however, is we can say redefine foo, and now we want to intercept the method bar and return hello world. And then down here, we're using a class reloading strategy instead of the previous class loading strategy, and that's basically using a Java agent. I'm showing you what that is in a second. But as a result of just running this code, the foo bar method call will return hello world, and this will assert validly, right? And obviously, you might wonder, like, what is this good for? I mean, it's good for annoying everybody on your team, because this is not very debuggable, right? This is not very intuitive either. And you can abuse this really, really well, but you shouldn't. What it is, however, good for, and that's the major use case, is that you are, for example, running an integration test. And the integration test is using some library that you cannot change, right? So and this library has some web service call at some point. Then you can either mock out the entire web service thing, or you just redefine the method that's calling the web service to just return a value. And then you're using this code, you redefine this call that you don't have control of, and you're done, right? That's all it needs. It saves you hours and saves you a lot of trouble. So, and you can, of course, the class reloading strategy also allows you to reset a class. So, in this context, it's super neat, right? There's one downside, though, and the downside is that you cannot define new methods. You can change anything. You can, for example, remove a modifier. If a method is synchronized and you want to remove the synchronized modifier, the JVM won't let you. There's, however, JEP, so-called enhanced class redefinition. So at one wonderful day in the future, we hopefully can use hotswap to just do anything. Remove methods, add methods, change interfaces. So it's a work in progress, but it's a work in progress, right? So there's hope. However, even today you can use much more advanced features, and this is writing so-called Java agents. And Java agents are a standard API that the JVM implements. Every JVM implements that, and I want to stress that out because it's not like a magic feature that is basically hacking into the internals, calling unsafe. It's nothing like that. It's a standard API. And we can do the same thing that we did before. Instead of bar, we want to return hello world again here. So how would a Java agent doing that look like? Well, it fits on the slide, so it's not so complex. A Java agent basically is like a Java program, but instead of a main method, it has a pre-main method. And the pre-main method, it's called like that, obviously, because it's called before main, right? So this is just a Java program that you append, or prepend rather, to your Java program. That's, however, not the only thing. The other thing is that it takes different parameters. And you still get an argument, not an array, just a single one. But then you also get an instrumentation instance. And the instrumentation instance offers you hooks into the JVM that are standardized. And one hook is a so-called class file transformer, where you can change any class that you want to anything you want. And this works for all classes, and also if you change the class that you're manipulating. So in this case, we can say, you want to create a new agent builder, that is a Byte Buddy API, and then we want to rebase any type named foo. In this case, this is the type above there. And then we want to transform it to basically take a build, we have a builder then, and then we end up in the same API that I showed you before. We say method named bar, intercept, hello world, and then we install this Java agent on the instrumentation instance that we got from the Java agent. And that's all you need. Now, if you run the program, this assertion will run true, because the Java agent is active. It will see once the foo class is loaded, oops, that's something I want to change, so I apply this transformer. So I take the method bar, and I return hello world for this method. And Byte Buddy does everything for you. You don't have to worry about it, and it works really well. So I think I'm reaching soon 500,000 downloads, so this is proven to work in practice. There's a lot of companies that use Byte Buddy. It's Google started using it. This is something you can use, I want to say. It won't break your code. It sounds scary, right? There's so much magic going on, but the JVM isn't magic. It's just bits and bytes in the end, and Byte Buddy just changes some of the bits and bytes for you. Yeah. So, and this is two different jars. That's the important part. The only thing with the Java agent is that you, in the end, you have to put in its own jar file. It has its own manifest. But instead of having -classPath jar file, you write -agent class file. That's all you have to change in your program, really. Then this is triggered. The agent is still available on the class path. You can have the very same jar being a normal Java program and a Java agent at the same time. Then it just has two methods, and they will be triggered in the order, with pre-main first and then the main method after. Oh yeah, I have color here. Right. So, where do I want to go with this? I have 5 minutes left, so I'm almost done. Right now, we have this Java space where we build a lot of software around infrastructure, right? We have Java EE, or we have Spring in the middle, and then we behave towards the APIs of these frameworks. And in the end, we have to, because in order to use our security framework, we have to use Spring Beans. And in order to have a Spring Bean, we have to register the class and the instance in the Spring container. So every code that we write has the container interaction to some extent. If you did a good job, you reduce it to some minimum such that the business logic still stands for itself. So this is how most programs are written. With Java agents, if you have libraries, if people like you, for example, took their time and wrote a good security library based on Java agents, you could invert this dependency. You could come and say, okay, you know what? I'm just writing my program. I still can use these annotations. I can even run my program without having the security profile active. So you can have a test container where none of the security is used, right? Because you're just not having the Java agent there. The annotations are ignored, right? And now you have this metrics library that collects statistics only if the Java agent is present. If it's not present, your program behaves as if there was no statistics behavior at all, right? And then we could write what I like to call plain old Java applications again, if we use this API more. And I hope Byte Buddy enables you to do so. All right, before I'm almost done, just a quick overview. On Java, this all works great, because Java is very standardized. It's very, it's very well specified, and things are tested and behave pretty well. So we have the JVM, which is a stack-based JIT-compiled machine, and I explained before why this is important for cogeneration. And then we have Android, right? And Android is different in many ways. I'm not saying it's a bad machine at all. It's an amazing piece of engineering, but it behaves very differently, simply for practical reasons, right? Java was born in this world of applets, and everything needs to be compact, and that's why the stack metaphor was invented in the first place, right? The great thing about stack language is that every instruction is implicitly referring to the top of the stack. And that's very practical, because then the bytecode is small and your applet loads very fast, right? Today, nobody would do this anymore because applets are deprecated now, right? They're gonna get removed in the long run. So this doesn't make sense anymore from today's perspective. But for compatibility reasons, we still have to do bytecode in the way we do bytecode. On a mobile phone, however, you want to start up quickly. So size of the program isn't so big, such a problem. But the problem is rather startup time of the app. And if you have to do all the translation of a stack machine language to a register-based language, because all phones are register-based, more or less, not more or less, all phones are register-based, period, right? So you have this indirection. So if you start up a Java program on Android, then all this work has to be done, and it takes longer time to load. So Android said, okay, this doesn't work for us. We have to translate into the DEX format, where everything's register-based. But it's still just-in-time compiled. So you could, in theory, still do things that you do. But if you look into Dalvik, and if you look into Dalvik Bytecode, which is very different to Java bytecode, first of all, things were done very ad hoc. You can tell from the spec and everything how things are done. They wanted to get their platform out. They wanted to do it quick. They took Java, they ripped it apart and repackaged it, done, right? It's difficult to work with Dalvik. So it's even more difficult, rather impossible to work with Art, which is the new Android runtime, because the new Android runtime takes a Java program, compiles it completely to machine code, and then you don't have the bytecode anymore. So after installation, the bytecode is already gone. So you cannot do the same thing with machines code for the reasons I explained before. Also, even if you did something like it, you can just invent a new machine code all of the time. New machines are built, new machine code is implemented. You couldn't keep up. So in Android, none of this is possible, and none of this will ever be possible to the same extent as it is on the Java platform. I do, however, support subclassing for Byte Buddy, at least. With cglib it doesn't work, by simply runtime compiling into DEX using Android's compiler, right? So I'm just hitchhiking the compiler, I package it with Byte Buddy, the Android version of Byte Buddy, and then I just write a new program that contains the additional class files. But you cannot manipulate simply because the bytecode's missing, right? Okay. Now I'm really, this is really last slide. Some benchmarks. I'm not going to go deep into this. You can find them yourself. If you're performance dependent, then this is interesting because, of course, again, cglib is 16 years old. Javassist is 15 years old. They couldn't do the same things I could do, so I streamlined Byte Buddy a lot towards performance. 3B is the most interesting one, I think, which is you have a trade-off at cogeneration, like every cogenerator, any compiler, between how much time do I want to spend creating code and how fast is the created code going to be. And Byte Buddy clearly goes in favor of I want to spend more time creating efficient code because cogeneration is most likely something you only do once, but you run the generated code for a long time. So Byte Buddy is very inlineable, such that the JIT compiler has a very, it's very easy for the JIT compiler to remove the generation layer altogether, so your code will behave exactly as fast as if you didn't use code generation with Byte Buddy. So, but of course, benchmarks are tricky. This is all JMH harnessed, so if you want to look into it, please do, and tell me if something's wrong. And that's it, right? I'm Raphael. As I said, I'm a consultant in Oslo, so you're not that far away. So if you ever want to hire me, just ping me. You can find me on Twitter. That's also fair enough if you want to do that. Otherwise, check out Byte Buddy. Please tell your friends, your family about the framework, because I'm just one person. I'm not having an evangelism team around me that goes all over the world, so I'm dependent on other people telling people, right? Other than that, I have another framework that I don't promote as much, but it's still worth checking out if you work a lot with business applications. It's a document converter. Everything's Apache 2.0 licensed, so help yourself. Thanks so far. If you have questions, I have 4 minutes left. Yes? At the microphone. Otherwise, just shout out and I'll repeat it. Yeah.
Would it be possible to implement that using this annotation processing compiler plugins instead of?
Yeah, absolutely. And I did a prototype. If you go on my webpage, there's a link to my blog where I show something similar just for a logging framework. So basically, yeah, Byte Buddy just adds the code, right? And then it works. If that's all you need, then that's great, right? And you are completely separate. So yeah, there's nothing in the way. You can just change any code you want. So the question was, for those wondering, if you could do basically the redefinition for the security framework I showed before, and yes, you can. Yeah. Any other questions? Yes, back there.
Is there any security restrictions? Could you override final classes? Could you modify JVM classes or Java lang?
If you do subclass instrumentation, and obviously if you use Mockito, for example, you cannot mock final classes, because the Mockito doesn't use an agent, it uses subclass instrumentation, like most frameworks for convenience. So with subclassing, you cannot do that. The same goes for Spring, goes for Hibernate. You need a default constructor, in some cases at least. You need non-final classes, non-final methods. But with redefinition, none of these restrictions hold, because you add the code to the method that you change, right? And then there's no overriding, so there's no interaction with the signature. So that you have no restrictions whatsoever. The one potential restriction you have is when you interact with Lambda expressions, because Lambda expressions in Java aren't real classes. They're loaded by so-called VM anonymous class loaders, and they have different access restrictions. With Byte Buddy, however, I found a work around it. Instead of instrumenting Lambda expressions, I instrument the JVM classes that generate the code, and I just replace it with my own stuff, and then I can do it again, so it works. But no, that's a good question though. Subclass instrumentation has its limits. Redefinition has no limits that I know of. Any other questions? Yes?
This all happens at runtime.
Yes. Yeah, you can. You can always use annotation processes if you need that, and then you have to hook into the abstract syntax trees generated by Javassist. You can, of course, write a Maven plugin, for example, and do stuff there, since in the end you're just deploying a different artifact, right? However, the cost of runtime code generation are so minimal, you can generate 10,000 classes in a second approximately. So if that's if you have a really close benchmark restriction that you have to start up in so and so many milliseconds, that might be a problem. But if you just make one database call, you can, with the empty cycles, you can just use them for that, and then you're good. Yeah. Yes?
Is there a difference between this and, say, aspect programming?
Yeah, the major difference is that people don't like aspect programming, so I don't try to brand it that way. But in the end, that's what you're doing, right? But It's more general. I don't like the aspect-J abstraction, this join points, point cuts. I don't find it intuitive. So there's this aspect-oriented programmer groups, and yeah. So I considered it, but I didn't like it, so I did something else. And I mean, I'm not a big fan of standards because you cannot you cannot do something different, right? And sometimes the original idea is not as good as the lessons I've learned from looking at aspect-J. So you don't need tool integration, for example. If I need tool integration, I would not only maintain the library, I would maintain an IntelliJ plugin, I would maintain a Maven plugin, I would have a Eclipse plugin, and then suddenly 90% of your time goes to plugins and not the framework. So I opted out in a way. But in the end, yes, it's aspect-oriented programming, but I won't call it like that. Yes?
You always start with type language, and people are usually using the static type language. You know what to compile and security, so verify that the law is. And then it shouldn't be anything different than what you want.
I mean, yes and no. So for disclaimer, I'm not doing anything. You're using my library to do it, right? And obviously you can abuse Byte Buddy tremendously. And the ideal use case is that you just change behavior in a way that doesn't affect the outcome. Like the security library, you just throw an unrecoverable exception. You shouldn't have called this method in the first place, but there was some leak in your program, some defect that some attacker, for example, found a path, an execution path, to come to this method from the outside, but it wasn't supposed to be happening. So you have this tight security abstraction then, where you, instead of having the error of deleting everything, have the error of the attacker getting a screen saying this is not happening, right? Obviously, if you, instead of deleting everything, you fill the database with anything, right? This could also be something you can instrument into the code, but then you're doing it wrong, right? So it's always, you can always break things. Oh yeah, sorry. I mean, yeah. Security and library or module encapsulation in Java is a difficult topic as such, because of course you can use security managers also to shield against intrusive code. You can, for example, forbid reflection to a library, because then you can manipulate state that you shouldn't manipulate. You can, for example, hook out something that was supposed to protect something. But the reality of Java is that, I don't know if you were lucky to work with a WebSphere application where you have like this big security overlord manager. In the end, nothing runs with a security manager, almost. If you forbid a library to do reflection, there's like 99% of libraries that won't work as expected anymore. So trusting code is something we need to do almost. And if you want to find an attack vector to a program, and that's something I also work with sometimes, there's easier paths than abusing a code generation library. I mean, there's like Hibernate, for example, uses Javassist, right? And Javassist works by compiling strings. And that leads to obvious attacks that are similar to code injection, SQL injection, right? So instead of injecting drop table, you inject system exit. And that's possible because Javassist just compiles the string, calls the method, done. But in order to prevent such attacks, you have to shield the generation layer. That's where you want to work with. And in order to shield the generation layer, you obviously have to know what the libraries are doing. But if Spring was corrupted, right? If you had a corrupt Spring jar, you're already vulnerable. Like, it's too late. You can't encapsulate Spring out of your database, for example, because basically Spring is the abstraction layer to access your database in the first place. So you're not secure once your libraries are corrupted. That's simply the reality. The security manager, in fact, it doesn't really work. It was a good idea, well intended, but it doesn't really work, in my eyes. So you're free to disagree, obviously. But all right, any other questions? Great, then my time's up anyways. I brought stickers of Byte Buddy if you want to take any. They're here on the table. Otherwise, I'll be here until this evening. Just find me if you have anything you want to talk about. Thank you.